Good afternoon, everyone. We will briefly report some of the results from this project. EPSRC is, for those of you who don't know, is one of the main, it's Engineering and Physical Sciences Research Council, which is one of the main bodies in the UK that is giving money for research. And we were lucky to get one 3 years ago, and we're soon about to complete the project. So we will now report, as I said, some of the results, but before that I will show you the evolution of the deep learning models that we developed for the prediction of adverse birth outcome. So briefly, I will mention the data sets that we're using. They're Oxford data sets. One is a bit older, one is a bit more recent. And then, as I said, Tony will tell you more about the results and interpretation, and more importantly, what is next. So, two data sets. The older one is about 60K samples. So after cleaning and getting rid of poor quality ones, we used about 44,000 for training testing. And the thing is that it's very unbalanced. The severe compromise cases are just under 1%, under 2% in both of that. And we try to keep the same distribution in the data subsets that we used in the training process. And at the bottom, you will see the more recent one of about 30,000, from which we used a bit above 22,000 cases. Again, the distribution, we try to keep the same percentage between the different classes. The labels that we use, most of the, widely adopted. So the distribution, again, you can see severe is less than 1%, and the acidemia a bit above 2%. Okay. So we started with the bottom model, which is simple linear, so-called convolutional neural networks. And then we upgraded it, combining it with so-called long short-term memory neural networks, which are good in picking up temporal characteristics. And we just then made it parallel, the two type of architectures combined. And subsequently, something that some of the previous presenters talk about. Now, long short-term memory neural networks are very good in picking up temporal characteristics, and because we have time series, obviously, we're expecting that to be good. Convolutional neural networks are very good in image recognition, picking up spatial characteristics. So that's the idea behind actually converting the input signal, the FHR signal, into spectrograms and scalograms using these Fourier and wavelet transforms, and then feed them as an input to the second flow in the architecture, which is based on convolutional neural networks. And as I said, they're very good to pick up these spatial characteristics. I have to say, I don't know how happy the previous presenters were with their results, but we expected to get much better improvements in the overall performance of the model than while in fact we didn't really get something significant as improvement in the metrics that we used for assessment. And then this is the final, I would say, or model, which incorporated multi-head attention mechanisms. Someone as well earlier mentioned this, that are very good in picking up long and short-term time dependencies. And the results that we obtained, I also have to mention that, well, in this table, just to see that we use some of the well-known derived from CTG characteristics as signal stability, long short-term variability, accelerations, decelerations, etc. And I will give the control to Tony to say a few words about some of the testing results, if you don't mind.
Thank you. I think I was supposed to take next one. So
Okay. Oh,
it's
yeah.
fine.
Okay.
I
just
think
we have
let me remember.
tested several models actually. These abbreviations, there's a random forest, XGBoost, multi-layer perceptron to compare with our multi-gap attention architecture. So yes, Tony was going, and these are just comparative figures to show the comparative analysis of the performances.
Okay.
So you can move to the
I'll just simplify. Let's see. How do I figure it out now?
if you point to the
Yeah, anyway, so just to spell it out a little, so we also similarly to the McHugh group look many minutes earlier, and here this is up to 2 hours before, but sometimes we go longer. And what we're looking here is the sensitivity if we cap the false positive rate to 15%, which is in our data sets tends to be the clinical intervention rate. So that includes forceps and ventouse and cesarean sections for fetal distress particularly. So yeah, and we were comparing to non-deep learning machine learning methods. So for the clinical audience, all of these things show that the black one, which is the deep learning method here, is reaching higher sensitivity throughout compared to all the other shallow. That's why we talk about deep from now on, and that's why we have session deep learning rather than shallow learning. So that's kind of the sensitivity you can expect to improve at least 10%, and so. I'll move on. Sorry. So I think these are, it's whatever I do, it's moving further. Okay, found it. So this is a lot of numbers, but those of you who followed our work, you see the first one is showing the data that was published in that ACTA paper 2017. So it's talking about OXIS 1.5, which was a very basic decelerative capacity, very basic metric, not even machine learning, and was comparing to clinical benchmark, which was again that that intervention rate for presumed fetal compromise, whether it's forceps, ventouse, or C-section. And you can look at the sensitivity again at a capped or similar false positive rate around 15% plus minus. So in our clinical set, in terms of clinicians acting on the CTGs, the sensitivity is only around 33%, so that's what you see there. And OXIS was very, very basic, was already outperforming this, and it was including just a couple of clinical risk factors, meconium and preeclampsia. And then that deep learning model we are presenting here on a testing set, so this means it's CTG data that the model has not seen before. So thousands and thousands have been used to train a model, but then we use 6,000 that have been set aside that are representative. And then this is the testing rate. You can see that we start reaching 51.5% sensitivity. So it's kind of reaching these numbers that would start making sense clinically to be so much better than the current clinical care or the basic non-deep models. But then we've been testing further on 22,000, so this is the newer data set. So if we put it again as a testing set only without being synced by the machine, we can see we lose some of that sensitivity when we get to 45% down there, and this is to be expected to a degree, but there are further things we can do to improve that, and we are doing them at the moment to kind of also train on parts of that newer data set, because that's spanning much later. It's another decade of data, and you can see how there are many differences in the way the clinical care was performed, as well as potentially the types of clinical outcomes and compromises that you may be having there and so on. But it's very interesting to dig into this kind of things and see what the differences are. And at the bottom, we of course always recommend the Brno dataset, for which I'm still very grateful for its existence. Thank you. That is very good to compare on. So we are always having quite a high sensitivity there. It's only acidemia in that data set. although some of the babies are severely compromised as well. But this is the so whatever we are doing, we tend to perform quite well on that data set. It's not a proper cohort, it's a selected bad cases and worst cases. But anyway, so these are the kind of numbers we like to look at, if I know how to move forward. Yeah, and these are, I'm not sure how to dwell on this, but so these are some further plots that we've been playing around the similar data sets that I showed. Now, if you go up to 12 hours earlier, how is your false positive rate increasing if you use different thresholds, and how is the sensitivity increasing? And again, if we bundle together acidemia with or without severe compromise and severe compromise, that's the first graph there, as a training set and then as a testing set. So what you're looking at, the graphs that are climbing quickly, that's that sensitivity. And you want to see how early you're able to predict them. So you can talk about 6 hours earlier, what is your sensitivity, and so on. These are preliminary data, and there are further things that we are doing to improve them. You can see that when we focus on severe compromise on this end, so this is all of them together, anything abnormal, as we call it. And now if we focus on severe only, you can see that the training data sets, these are the circles, was actually performing really, really well. It's again testing set. So it was used to train, but then we are only showing the data on the 6,000 testing set. And you can see how we are reaching sensitivity of 20% and above very early on, which means that 1 in 5 of the severely compromised babies we could flag 8 hours or 7 hours earlier without a very high false positive rate at all. However, we don't replicate that result in the 22,000 much later decade data set, and you can see we are doing something, but it's not great. However, for acidemia, we are, if you look at only at acidemia in that figure there, you can see that actually the 22,000 testing set, that it's spot on as well, the sensitivity, and the false positive rate is a little bit higher there. So that's generally great result, means that the model, even though it's a deep learning, it's kind of like more complex, is learning the right things, if you wish, but there is certainly room for improvement around the hard outcomes, and we are doing work on that. And I think that was the main. I think Ivan wants to talk about the conclusions. Thank you.
Not a lot, but just Peter earlier mentioned that they would like to consider not only mother, but the fetus characteristics as well. So in our follow-up project, because all that we use so far is either CTG or derived from, as we showed some of the characteristics, derived from CTG records. So the idea is in the follow-up project to implement, to incorporate more holistic approach that includes additional characteristics about the overall mother well-being in lifestyle, fetus additional characteristics, but also features related to the labor ward environment as well, including even parts from related to the data storage, data processing, security, etc. So that's the team that is working on the project. Thank you, and just to add that on Wednesday afternoon we will be looking for expression of interest to join the team for the next proposal, which is intended to be under this Horizon Health program, which is very, very well funded. And UK just rejoined it after Brexit from the beginning of this year, so we hope we have a good chance to get it. Thank you for your attention.